All right, today we're going to talk about chemistry. It's important that we have at least a basic lecture on chemistry so we can understand the chemical processes that happen throughout the body. We have tons and tons and tons of chemicals in our body, and they make all sorts of chemical reactions happen and processes happen in our body. So it's really, really important that we understand. Hopefully some of you have, had chemistry classes, or maybe have taken a chemistry class in college, so this isn't the first time you're being exposed to some of these things. So basic definitions here: matter has mass and occupies space. Elements are what we consider pure substance, so both elements and compounds actually make up matter. But the difference between an element and a compound is an element is a pure substance. Even though we're going to talk about elements being made of electrons, protons, neutrons, it's cannot be broken down any farther. Even though it is made up of protons, electrons, and neutrons, it can't be broken down into those things. So an element is a pure substance that cannot be broken down. Some examples include oxygen, hydrogen, versus a compound is a chemical combination of two or more substances. So that example would be water, where hydrogen and oxygen come together to form a compound called water. The major elements of the body are oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. Those are the ones you need to know. There's a total of 92 elements on the periodic table, 24 of which are important to the human body. The major elements make up about 98.5% of body weight. And of those major elements, oxygen actually makes up about 65% of our body weight. So oxygen is huge. But usually these elements don't exist by themselves. They combine with other atoms to form compounds. I want to show you for a second the periodic table. Oh, geez. So hopefully we remember this a little bit. It's probably been a little while since we've seen this, but sorry, I'm trying to make it fit in the window here, but of course it just doesn't want to. So it's the periodic table of elements. Refresher here: hydrogen, sodium, magnesium, potassium, calcium. You do need to know those abbreviations. You need to know carbon, nitrogen, oxygen over here. Chloride is here. If you scroll to the bottom of this, you can see that it talks about metals versus nonmetals. Usually the metals are on the left side of the periodic table. Nonmetals are over here. And those combinations usually come from one element on each side of the table. Our lesser elements make up about 0.8% of our body. There's not too many of those. The ones I want you to know are sodium, abbreviation Na, potassium, abbreviation K, chloride, abbreviation Cl, magnesium, abbreviation Mg, and iron, abbreviation Fe. Those are our lesser elements. And we have trace elements. Those are manganese, zinc, iodine, and copper. I don't expect you to memorize those at this point. Elements are made up of three things: protons, electrons, and neutrons. Protons positive, electrons negative, neutrons neutral. So if you can remember neutrons, which almost sounds like neutral, and proton starts with a P and is positive, then you can figure out that electrons are a negative charge. I think it just helps people to put that to memorization sometimes. We're going to talk about how these come together to form one element. Okay, this is one element here. There's a couple of things we need to know about this. Protons and neutrons are in the nucleus. Electrons are outside in these kind of concentric circles out here. They just kind of float around and whirl around the nucleus. It's important that we know that in the first energy level, or this first level here, you can only have 2 electrons. In the second level, you can have 8. The third level, you can have 8 as well. Atoms always, or elements, are always trying to become stable. They're stable when their outer ring is full. So they're actively always trying to achieve that. And so when we talk about bonding here in a minute, that's why these elements often bond, is because they want to become stable. And at their normal state, often they're not stable. So I'm going to show you an animation from Davis Plus. And again, you can watch this. It's on Davis Plus. So if you set up your Davis Plus account, you'll be able to watch this.
Anything that has mass and occupies space is called matter. In turn, matter consists of either elements, which are pure substances that can't be broken down into two or more substances, or compounds, which are chemical combinations of two or more elements. Water, for example, is a compound formed by the combination of two atoms of hydrogen and one atom of oxygen. Hydrogen and oxygen are elements because they cannot be further broken down or decomposed chemically. Elements consist of particles called atoms. Atoms, in turn, consist of even smaller particles called protons, neutrons, and electrons. Protons, which have a positive charge, and neutrons, which are electrically neutral, are packed together in the center of the atom called the nucleus. The number of protons in the nucleus determines the element's atomic number. For example, hydrogen has 1 proton, so its atomic number is 1. Oxygen has 8 protons, so it has an atomic number of 8. Whirling around the nucleus are one or more concentric clouds of electrons, tiny particles with a negative charge. Each ring around the nucleus represents one cloud or shell. The number of shells varies between atoms. For example, hydrogen has only 1 shell, whereas oxygen has 2. The heaviest natural element, uranium, has an atomic number of 92 and 7 electron shells. Each shell can hold a certain maximum number of electrons. The shell closest to the nucleus can hold 2 electrons. Each of the outer shells can hold 8 electrons. Once again, atoms consist of light negative electrons, heavy positive protons, and heavy neutrons. In turn, atoms build up elements and compounds, which combine in various ways to form matter.
I really like those animations from Davis Plus because they do a nice job of giving you a visual along with reinforcing some of the things we talked about. So I really like using those, and then you guys can have access to them all the time. So he talked a little bit about atomic weight, atomic number, those types of things. Each element carries a unique number of protons, which is what makes it the element. So it's important that we are able to differentiate that. Atomic number equals the number of protons in the nucleus, and atomic weight is the number of protons plus the number of neutrons. I'm going to talk about chemical bonding, ionic, covalent, and hydrogen bonds. I'm going to focus mostly on ionic and covalent bonds. What I want you to understand about chemical bonds in general is that they're not structures, but rather a force or attraction between positive and negative charges. You're going to really be able to see that pretty quickly via ionic bonds, I think. But really what happens during chemical bonds is 2 or more atoms join and they form a molecule. And then we start to get these compounds and things like that. Like I said a few minutes ago, they want to bond together because they really want their outer shells to be stable. And what did I say about their outer shells being stable? That first electron ring has to have 2 electrons in it to be stable. Then the second one has to have 8. The third one has to have 8. So if the element only has 2 electrons, they're both in its inner shell, it's stable. If it has 4, though, it has 2 in its first ring, 2 in its second ring, is it stable? No, it's not stable because it doesn't have a full outer shell of 8. So they're always trying to achieve that full outer shell of 8. And you're going to see that here with this sodium and chloride molecule. Sodium has 1 electron out here in this outer shell, and it doesn't like it. You see how it has 2 here, 8 here, but then it's got this 1, and that makes it not very stable. Chloride, on the other hand, has 7 in its outer shell. So it's a natural fit for sodium to pass one of its electrons over to chloride, and then they both are stable because they both have outer shells. Okay, so they actually they transfer 1 electron to the next. And what that does is it actually changes sodium to be positive and chloride to be negative. Because sodium is giving away one of its negatively charged electrons, it becomes more positive. Chloride, on the other hand, is gaining that negatively charged electron, so it becomes more negative. What happens here is once these elements become positive or negative, we actually call them ions. And we're actually going to talk about ions all throughout nursing school. So it's important that we understand how these ions are formed. Atoms or ions with a positive charge are called cations. Okay. And atoms with a negative charge are called anions. So you need to definitely understand those definitions and be able to differentiate those two things. So what happens is once they become positively and negatively charged, then they actually get this electrostatic force that draws the two atoms together, forming an ionic bond. So sodium and chloride come together to form what we know as table salt. These ionic bonds, one of the properties of ionic bonds is that they break down when dissolved in water. So they dissociate, we call it. So if we put salt into water, it's going to break apart again into sodium and chloride ions. So that's one of the properties of ionic bonds. Covalent bonds, on the other hand, are formed in a different way. They actually share one or more pairs of electrons. So in ionic bonds, they actually transfer the electrons. Here they actually are going to share. Covalent bonds always occur through the sharing of multiple electrons, and carbon usually always is involved. A carbon atom usually, here you can see one carbon atom shares one pair of electrons with two oxygen atoms, completing the outer shells for all three. So again, in covalent bonds, they're looking to become stable and they're looking to make that outer ring full. So you can see here that it has this oxygen atom has 2 electrons in the inner circle, 4 electrons in the outer circle. But by sharing these 4 here, it gives this oxygen atom 8 in its outer shell, right? Carbon atom 2 on the middle. And by sharing on both sides, you can see how it has 8 in that outer circle. And again, then the oxygen over here. So these are actually what we call double bonds because they're sharing 2 sets of electrons there. If it was a single bond, you would only see 2 electrons there instead of 4. But in order to create this, this is called a carbon dioxide molecule, right? 1 carbon, 2 oxygen. That's how it works. Covalent bonds are stronger than ionic bonds. They create a lot of chemical structures in our bodies. Proteins and carbohydrates are formed through covalent bonds, and they do not dissolve in water like our ionic bonds do. So I want to, again, show you a little clip on this from Davis Plus. So this time we're going to watch this chemical bonds here.
Each atom consists of a nucleus and 1 or more electron shells. An atom's outer electron shell can hold a maximum of 8 electrons. An atom with a full outer shell is said to be stable. However, most atoms are not stable because their outer shell is not full. These atoms attempt to lose, gain, or share electrons in their outer shells to become stable. They do this by forming chemical bonds. 2 types of bonds are ionic and covalent bonds. Ionic bonds are formed when one atom transfers an electron from its outer shell to another atom. Because electrons are negatively charged, when an atom gains or loses an electron, its overall charge changes from neutral to either positive or negative. Electrically charged atoms are called ions. The positively charged sodium ion, Na+, is attracted to the negatively charged chloride ion, Cl-. The electrostatic force draws the 2 atoms together, forming an ionic bond, which results in sodium chloride, or ordinary table salt. In covalent bonds, instead of transferring an electron, 2 atoms share 1 or more pairs of electrons as they attempt to fill their outer shells. For example, if 2 atoms of hydrogen share their electrons, their inner shells would be full. Thus, a single covalent bond exists and hydrogen gas, H2, is formed. Double covalent bonds may also occur, in which atoms are bound together through the sharing of 2 electrons. For example, when one carbon atom shares 1 pair of electrons with each oxygen atom, a molecule of carbon dioxide is formed. Both ionic interaction and covalent interaction result in a molecule, a particle composed of 2 or more atoms united by a chemical bond. The microscopic world of atoms and molecules forms the foundation of life.
So a little more detail there. And really, I want you to understand the difference, okay? So ionic bonds, they actually transfer the electrons. Covalent bonds, they actually share the electrons. Though that's kind of the main difference, okay? Hydrogen bonds, on the other hand, I just want to talk about very, very briefly because it's pretty complex, and I feel like the other two are really a little bit more in depth. So hydrogen bonds actually don't form a new molecule. Hydrogen bond is just a weak attraction between a slightly positive hydrogen atom in one molecule and a slightly negative oxygen or nitrogen atom in another. So water is an example of how hydrogen bonds form. Water consists of 2 hydrogen atoms bonded with covalent bonds to an oxygen atom. In the bonding process, oxygen shares 2 of the electrons in its outer shell with hydrogen. Even after bonding, it has 4 additional electrons in its outer shell. These unpaired electrons give water a partially negative charge near the oxygen atom, so over here, okay? And then the slight positive charge on this side. So this is really about molecules kind of bonding together. This is what we consider a polar molecule. So within one molecule, we actually have one side of it that's slightly negative and one side of it that's slightly positive. So a hydrogen bond, what happens is 2 water molecules are actually slightly attracted to each other because on this side it's negative and on this side it's positive. So again, positive and negative charges actually attract a little bit, and we get water molecules to form these hydrogen bonds with other water molecules. And water is really, really important in our body. So again, this is important, but that's really all I want you to know and kind of understand about it. To function, the body needs energy, right? I don't think that's probably a surprise to anybody. And energy is stored in the bonds of molecules, so that's why we're going to talk about it here. That's actually considered what we call potential energy. So we have this energy stored within a bond. Chemical reactions release the energy, and then energy is what we can call in motion, and that's called kinetic energy. Once it's released from that bond, it's kinetic energy, okay? So an example of this is potential energy is the bow and arrow being pulled taut, and then kinetic energy is when the bow is sailing forward or the arrow is kind of shooting out of the bow, right? That's actual energy being used, whereas when you just pull it taut, it's just potential energy. So it has the potential to create energy. Metabolism is really all the chemical reactions in the body are what we call metabolism. And it's important that we understand these 2 different terms. Probably heard these before, but catabolism and anabolism. So catabolism involves breaking down complex compounds such as large food into simpler ones. And these reactions release energy. So this is a breaking down of large compounds or molecules into simpler ones. Versus anabolism involves building larger and more complex chemical molecules from smaller subunits. And anabolic reactions require energy. So catabolic reactions release energy, anabolic reactions require energy. So the 2 differences there. Hopefully you're going to hear more about metabolism as we continue in this and as you have your nutrition lecture in fundamentals. Most of the molecules of the body form organic compounds. Organic compounds contain carbon. So if anyone's ever heard of like organic chemistry, it's really all related to carbon. Versus inorganic compounds include water, oxygen, carbon dioxide, and acid and bases. So you have to understand organic compounds contain carbon. And we're going to talk about why that's important that we know that. First, I want to talk just quickly about a couple of different chemical reactions. So not chemical bonds that we talked about a few minutes ago, but chemical reactions. This involves the formation or breaking, sorry, a little typo there, of chemical bonds. They're really expressed as chemical equations. You'll do a little bit of this review of this in class. But on a basic front, you need to understand these things. A synthesis reaction is A plus B comes together to create one thing. Okay? Take your peanut butter, you take your jelly, you put it on your bread, and you put them together. That's a synthesis reaction, right? We have our peanut butter, we have our jelly, it comes together as a peanut butter jelly sandwich, synthesis. Decomposition is a bit different. So it's when you have one complex substance and then it becomes broken down into smaller things. So this is when food goes into our digestive tract. Say the peanut butter and jelly sandwich goes down into our digestive tract. It gets broken down again into not necessarily peanut butter and jelly, but all the molecules that make up peanut butter and jelly. And then exchange is just that, an exchange. So we have A and B plus C and D, and then we get this AC plus BD. So there's really just a swapping kind of molecules there. Synthesis and decomposition are really the most important ones that we understand there. And it's important that we understand that these, certainly you can see that synthesis and decomposition can go backwards. They're just the opposite, right? Synthesis is coming together to create one. Decomposition is breaking down. Water has plenty of unique characteristics. Number one, it's a solvent. It can ionize large chemical compounds and transport them to cells. Water compromises about 50 to 60% of an adult's body weight, so it fulfills so many different roles in our body. It's a lubricant. It lubricates our lungs. It lubricates our GI tract. It certainly lubricates our mucous membranes, which is probably something that you're all familiar with. You have saliva in your mouth. That's a lot of water. And it changes temperature slowly, so it helps us to mediate our temperature. It can absorb heat. It can give off heat, and it allows us to maintain a stable body temperature. Almost all metabolic processes in the body depend on the solvency of water. So that's why it's really, really important. And it's important that we stay hydrated and we have a balance of water within our body. Body fluids, they're fluids in the body consist of chemicals dissolved or suspended in water. So we're going to talk about all sorts of body fluids coming up. We're going to talk about plasma. We're going to talk about lymph fluid. All sorts of different things, but it's really just a bunch of chemicals dissolved or suspended in water. And as we dig deeper into those different body fluids, we'll really figure out, well, what do they do? A compound, the definition of a compound is when two or more elements combine to create a new substance. Okay, so sodium and chloride are actually poisonous by themselves, but when they're together via the ionic bond, they form table salt, right? NaCl, table salt, and that certainly isn't very poisonous to us. So we have tons of compounds within our bodies. One other thing is a mixture. So a mixture is a bit different than a compound because a mixture really results when two or more substances blend together rather than chemically combine. So something like scrambled eggs in which you add salt to, the eggs and the salt remain just as they were, right? Eggs and salt, they just happen to be together. Versus a compound, like we talked about, is sodium and chloride coming together and they actually become something different. Oxygen is an inorganic substance involved in the process of cellular respiration. We'll talk more about that. But really, oxygen, all of our cells need oxygen to break down nutrients to release energy. It's a vital part of our body. I think we all think about that. That makes sense, right? We have to be breathing. We have to be taking in oxygen in order for our body to survive. And that's because the oxygen is essential for these nutrients to be able to be broken down and to release energy for our body to work with. A little known fact is room air, which is the air we breathe in all the time, we call that room air, is about 21% oxygen. When you start going in the lab and we start talking about respiratory equipment and oxygen, that's going to be a much higher percentage of oxygen coming from those wall units when we give our patients who are not getting enough oxygen. Carbon dioxide is a waste product of cellular respiration. So as those glucose and those nutrients are being broken down to release energy, a waste product of that is carbon dioxide. So we have to be able to get rid of carbon dioxide, and that's one of the main functions of the lungs. We breathe in oxygen, it's transported to our tissues, down to our cells. Then our blood picks up the carbon dioxide, which is the waste product, and when we exhale carbon dioxide. So you can see how just talking about these elements here, how much further we're going to get into depth of them when we start talking about all of the different systems. We need to talk a little bit about acids and bases, and we are going to do a little activity in class about this, so we'll get to actually test out this pH scale. But we need to understand what makes acids acids, what makes bases bases. Okay, so really hydrogen ions are what we consider an acid. So acids release hydrogen when dissolved in water. So you can see here that this is HCl, hydrochloric acid. When it goes in water, it actually completely dissociates and becomes hydrogen ions and chloride ions. The more hydrogen produced, the stronger the acid. So you can see that there's a fair amount of hydrogen there. That's a pretty strong acid. In contrast, a weak acid doesn't completely dissociate when it goes into water. So you can see there's still some molecules over here that are together, and you get much fewer hydrogen ions kind of circulating around, or called free hydrogen ions. So it's much more of a weak acid. So down the road, we're going to talk about the respiratory system again, and the kidneys and the renal system. We're going to talk about acid-base balance because those systems play such a role in the acid-base balance in our body. We're going to talk a lot about hydrogen ions, and I'm going to say if we're getting rid of hydrogen ions, are we going to become more acidic or more basic? And we're going to really, have to make that connection. For now, I just want you to understand really the difference between acid and bases. So we talk about bases, we're going to talk about OH negative ions, okay? And those really is considered a base because it can accept hydrogen ions. So this Na sodium ions plus the OH ions, sodium hydroxide is what it's called, dissociates in water into sodium and OH. And then what happens is you can see that we consider it a base because it can accept those hydrogen ions. So we can dump hydrochloric acid in here. Hydrochloric acid is going to separate or dissociate in the water as well. And then you can see that these sodium ions here can pick up the chloride ions, and the hydrogen ions are going to bond again to this OH. And what's that going to make? One hydrogen plus oxygen and hydrogen is going to make water. So it's a base because it accepts hydrogen ions. So that's going to be one differentiating factor for you. I'm going to show you another animation here on Davis Plus. This is going to be about acids and bases. And remember, these are all things that you can watch on your own. So you want to watch this again, feel free.
An acid is any substance that releases a hydrogen ion when dissolved in water. Because of this, acids are sometimes called proton donors. A strong acid completely dissociates into hydrogen and an ion. For example, when hydrochloric acid is dissolved in water, it dissociates into hydrogen and chloride. In contrast, carbonic acid dissociates very little and produces few excess hydrogen ions in solution. The fact that it produces few hydrogen ions makes it a weak acid. Bases, or alkaline compounds, are called proton acceptors because they accept excess hydrogen ions. Strong bases, similar to strong acids, completely dissociate in water. A common strong base called sodium hydroxide, NaOH, dissociates into sodium and hydroxide. If an acid, like hydrochloric acid, were to be introduced into the solution containing sodium hydroxide, the hydrochloric acid would also dissociate. The solution would then have hydrogen ions, chloride ions, sodium ions, and hydroxide ions. The hydroxide ions would accept hydrogen ions, forming water and reducing the acidity of the solution. The sodium and chloride ions would also combine to form sodium chloride, salt.
So again, just another example, just another way of explaining it. It's a bit confusing, I know, but we're going to talk more about it. What I really want you to understand is the pH scale, and we're going to do some testing of the pH scale. But it's important that we know that pure water is 7. So anything lower than a 7 on the pH scale is acidic. Anything higher than 7 on the pH scale is a little bit basic. So we really want to see where blood fits in here. And the actual pH range of blood, which you do need to know, is 7.35 to 7.45. So blood is always a little alkaline, or basic, we call it. But you can see on here there's all sorts of things. Bananas, tomatoes, acidic, lemon juice probably doesn't surprise us. Soda is really, really acidic, which is why it's so bad for your teeth. And we're going to do some testing of this, but you need to know pure water is 7. Anything less than 7 is acidic. Anything greater than 7 is basic. Blood pH range 7.35 to 7.45. And our body works really, really hard to keep that pH in 7.35 to 7.45. Okay, so we talked about inorganic compounds. I want to talk about organic compounds. Remember, carbon really is the basis for organic compounds. The compound has to contain carbon. But carbon can combine and do so many things. It makes thousands of different molecules of varying size and shape. The basic ones are going to be carbohydrates, lipids, proteins, and nucleic acids. You're going to talk more about carbs, lipids, and protein and nutrition, but we're going to very generally talk about it, and then we're going to focus most of our attention on nucleic acids and on ATP. Carbohydrates are the body's main energy source. Glucose is the primary form of sugar used by cells. All carbohydrates break down to become glucose. Even our complex carbohydrates eventually need to be broken down to be glucose so that we can use it in our body. Glycogen is the stored form of glucose. We don't store a ton of glycogen though, but we do have a little bit of it. But we really need to be active in eating carbs pretty much throughout the day. When our body breaks down carbohydrates, it releases energy. So that's why we need carbohydrates. Our central nervous system really can only use the carbohydrates as an energy source. So we have to keep this as a nice steady flow throughout the day. Lipids are a reserve energy supply. They provide structure to the cells. So next week, we'll talk about cells and we'll talk about the cell walls. And you'll see how lipids play a role in that. They insulate our nerves. They serve as vitamins. And they really cushion our organs. So lots of different roles lipids play. Lipids are kind of known as fats. So cholesterol, triglycerides, those types of things really are the most abundant lipids. You might hear talk about saturated fatty acids versus unsaturated fatty acids. Saturated fatty acids really form a solid mass at room temperature, and they're derived from animal sources. So a lot of lard is considered saturated fatty acid. If you've ever looked at a steak and you were able to see the marbling of the fat in it, that's a saturated fatty acid because it's solid, versus an unsaturated fatty acid is liquid at room temperature. These are things like olive oil, canola oil, coconut oil. It's considered saturated because it is solid at room temperature, but it kind of sits right on that edge, so it is one of the better saturated fatty acids. Proteins, they're the most abundant and important organic compound in the body. Proteins consist of amino acids. That's why they're so important. Amino acids play all sorts of roles in our body. There's essential amino acids and non-essential amino acids. But they break down, they're enzymes, they're hemoglobin, they're hormones, they're antibodies. They play so many different roles in our body. I think sometimes people think, protein, it's just in our food, right? Tuna, chicken, peanut butter, good sources of protein. But our body needs protein. It's not just that protein is filling and protein helps to decrease our appetite, which it does, but it actually plays a vital, vital role in our body. This is one amino acid. So there's an amine group, an R group, and a carboxyl group. The R group is what differentiates amino acids from each other. So all the rest of this is the same, and then each different amino acid has a different R group. But we're not going to get into all of that. Like I said, nucleic acids is what I want to focus a little bit more on. You do need to know proteins, carbohydrates, and lipids, but nucleic acids is a little bit more of some things we're probably not super familiar with. Nucleic acids include DNA and RNA. They consist of thousands of nucleotides. Nucleotides consist of 5 carbon sugar, a phosphate group, and one of several nitrogen bases. So in DNA, the sugar is deoxyribose. In RNA, the sugar is ribose. So you can see that they're similar, but they're different. DNA is the largest molecule in the body. It can be very, very long. It is really responsible for carrying genetic code. Probably all know that. There's been a lot of discussion about DNA over the last 10 or 15 years, and that my DNA is different than your DNA. The RNA, on the other hand, is really just responsible for copying the genetic code of DNA to direct protein synthesis. So it kind of assists the DNA. ATP is really important because ATP is what really produces energy. So an ATP is a nucleotide that stores energy. It consists of a base, a sugar, and a phosphate group. The phosphate groups are connected with high energy bonds. So this is where our energy really is going to come from. And you'll see what happens is when our body needs energy, a chemical reaction breaks this bond and releases energy that our body can then use. So we need to have ATP throughout our body at all times to help facilitate chemical reactions and syntheses throughout our body. I want to show you one last animation on it so that you can get a little bit of a better understanding of this.
Food provides the body with energy. However, even when food is broken down, cells cannot use it directly. Instead, cells tap into energy stored within a compound called ATP.
Sorry about that, guys. I had to pause it for just 1 second, so we're going to start this over again.
However, even when food is broken down, cells cannot use it directly. Instead, cells tap into energy stored within a compound called ATP, adenosine triphosphate. ATP consists of a base, a sugar, and 3 phosphate groups. The phosphate groups are connected to each other with high energy bonds. When one of these bonds is broken through a chemical reaction, energy is released that can be used for work, such as muscle movement, as well as the body's physiological processes. After the bond is broken, ATP becomes adenosine diphosphate, ADP, and a single phosphate. Later, using some of the energy released from the breakdown of the nutrients in food, the single phosphate is reattached to the ADP, again forming ATP. The renewed ATP molecule can now be used again.
All right, guys, so that ends our lecture for today. You guys should be all set to start reviewing things more thoroughly in your book. If you're confused about any of the things I talked about today, hopefully you took some good notes, and you should be ready to move on to hopefully take your pre-quiz, start participating in the discussion boards, and get ready for class during the week.